First of all, let's provide a little motivation for why do I need to know this. And I know you're probably not farmers. I'm not a farmer either, although some days I feel like one with all the animals at my house. But a farmer is, agribusiness is a business. And suppose you have an animal feed that's made from 2 ingredients, corn and soybeans. Now, 1 serving of each ingredient provides the number of grams of protein and fiber that are shown in this chart. And protein and fiber are something that animals need, farm animals need, in order to have a healthy diet. So the entries in the first column, 3 and 11, say that 1 serving of corn provides 3 grams of protein and 11 grams of fiber. And then that second column says that similarly, 1 serving of soybeans provides 10 grams of protein, but only 4 grams of fiber. And the reason that would matter is because you need to know how many servings of corn and soybeans could be used to make a feed that contains 115 grams of protein and 95 grams of fiber for one particular breed of animal that you're feeding. So you let X represent the number of servings of corn used, and the number of servings of soybeans is going to be Y. And the serving of corn produces 3 grams of protein, so the amount of protein provided by X servings of corn would be 3 times X. And then by the same token, if you're talking about the protein, then you have Y servings of soybeans will give you 10 times Y amount of protein. Now, you need the protein amount to be 115 grams. So you're going to add 3X plus 10Y to get 115, and you need your feed to supply 95 grams of fiber, so you have 11X plus 4Y equals 95. Now notice here in these 2 equations, X and Y represent the amount of corn and soybeans. That's the variable. How much corn do I need? How much soybean do I need? And then your first equation is actually about how much protein do I need? And your second equation is about how much fiber do I need? And you've got to find a common X and Y that solves both of those equations. Now, in truth, I'm going to tell you up front, dietary needs for a farm animal do not involve only 2 ingredients, of course. They involve several ingredients. So besides those 2 ingredients, we might have 3 or 5 or 8 variables. We might need to also be looking at the amount of fat that the food has, the amount of carbohydrate that the food has, the amount of a certain mineral or vitamin that the food contains. So you have to look at more than just these 2. So this is a very, very simplified, realistic example. So solving the problem means, as I said, we're going to have to find values of X and Y that satisfy what we call this system of equations. And we can verify that X equals 5 and Y equals 10 as a solution of that system, because if you have 5 pounds of corn and 10 pounds of soybeans, then that's going to actually create true solutions for both of those equations. And that's going to be the only solution in this particular case. The downside for most of us that are going to do the math on it is that there's not always one single solution. And in fact, sometimes there's no solution at all. And sometimes there is a solution. In fact, there's millions of them that would work. So in practical systems, we're going to have first degree equations. My goodness, can't talk tonight. We're going to have a system of first degree equations, which just simply says that all the variables have a power of 1. We don't have any quadratic equations in this. So those will be known as linear systems. Now, to picture the solution, one of the ways to solve the problem is to graph them. And I'm going to actually graph that problem by going back up and looking at those 2 equations. And we're going to verify that that solution actually is on the graph. So what I'm going to do is I'm going to go to Y equals, And since I need that equation solved for y, not x, then I'm going to write these down. And I'm going to show you a quick and easy way you can graph this without solving for y and doing all the simplifying. So here's the system of equations that we're interested in, and we want to put it in the calculator. So what we're going to do here is we're going to put in y1. The first thing we would do is we'll move the 3x over there with the 115, right? So that's going to give us 115 minus 3x. And then what we need to do is we need to divide by the 10 in front of the y. So we're going to divide that whole thing by 10. And then y2, we're going to do the same thing. We're going to start with the 95 that's already over on the right, and we're going to move the 11x over there with it. And then we're going to divide the whole thing, once again, by 4. Now you have to use the parentheses because you have to divide both of those terms. And no, I know that's not in y equals mx plus b, but that takes an extra step. And all I really want to do is look at the graph. So I'm going to enter 115, whoops, forgot my parentheses, 115. Let's try again. This calculator is so touchy. It either gives you no parentheses or bunches of them. Minus 3x, close the parentheses and divide by the coefficient of y, which is 10. And then for the second equation, I've got the 95 there already. I'm going to subtract the 11x from it, close the parentheses, and then divide that by the coefficient of y, which this time is 4. Now realistically, is there any reason to look at negative x or negative y values? X and y represent the amount of corn and soybeans. Are they going to be negative? No. So we should probably start at 0 for both of those. And that's the only thing I'm going to do to the window to start with, because I just want to see where, you know, potentially there might be a solution. So we're going to let it go from 0 to 10 in both directions and graph. And I notice one of my equations is there and there's the other one, but I clearly am not seeing all of the graph. What do I need to do to be able to see that whole intersection point? Does the window need to be taller? Does it need to go farther out on the y-axis? Okay, I need to raise up the y. So let's go back to the window and let's raise the y max up to 20 and see if that does it. So I hit graph again, and there goes my first equation. There comes my second equation, and now I can see all the values. Okay, I can see the complete intersection point. Now, the reason I didn't start out on this window, because I knew it wasn't going to show up on the first one, is because I'd already done the problem, but you're not going to know that. So what I want you to do is I want you to get used to setting your calculator window by looking at it's all going to be applications problems. So you need to look at your calculator and look at your problem and say, okay, realistically, where do I need to start? And if you're talking about an application problem, chances are x and y can't be less than 0. So start at 0. And then go ahead and graph and see if you see anything. If you don't see anything, then go to your x max and your y max and make that graph wider and make it taller until you do see something. Eventually you will. The other thing you can do, and I didn't do it on this one, but if I start out going 0 to 10 in both directions, because I'm trying to teach you the technology skills while we're learning the math. If I go ahead and start out on that window and I hit graph and I don't see what I want to see, another thing that I could do without having to think it through myself is just go back here to zoom and tell it to go down to zoom 0, which will fit. It'll take my existing X values and it will find a window that I can see both the X and the Y and the intersection points. So it made a little bit different window, but it still shows the complete intersection point. But the thing is, it wouldn't have showed you this particular graph if you hadn't known to start with X being 0 and Y being 0. So apply the common sense part of it. Now the solution is the one single point right there where they intersect. That solution works in both equations. And in order to find it, all you need to do is you hit second trace and choose intersection point. And hit enter. 3 times. The first one to tell it, yes, this is the right curve. Yes, this is the other line. And yes, you can guess. I trust you to guess. And it comes back and it says the answer is 510. 5 units of corn, 10 units of soybeans. Okay? So this is an example of a system that has one solution. Now, this is not from a realistic problem, but I want to give you an example of a system that has infinite solutions. And hopefully I just did that. I just did. We'll see if I was good. How many lines do you see? One, but I put 2 equations in there where I'm only seeing 1 line because of the ones on top. That's right, one's right on top of the other one. And the way you know that is if you hit your trace button, notice that this says it's on the first equation. But if I hit my down arrow button, it says, well, now I'm on the second equation. And the reason for that is because the first equation and the second equation are in just 2 different forms of the same line. Okay? Because the first equation is equivalent to the second equation in another form. So it's the same line. So that has infinite solutions. Okay? Now I'm going to change that second equation again. So there goes the first one. And there goes the second one. You think they're ever going to cross? No? I mean, I could extend it out and see if maybe they get closer together. But what's happening those 2 lines? How would you describe those 2 lines? They're running parallel to one another, just like a railroad track. So what happened was the equations that I put in 115 minus 3x divided by 10. And the second equation, the only thing I changed was that number. I changed it from 11.5 to 12.5. So 11.5 was 115 over 10, 12.5 is not. I gave it a new y-intercept, but I didn't change its slope. That's still going to have the same slope. So those lines are parallel. And that has no solution. Okay, that's what that slide's talking about, is that you can have three different things happen when you're talking about two lines. Either they're both the same line, one right on top of the other, or they run parallel to one another, or they cross. And if they cross, there's a solution. If they lay one on top of the other, that means everything that solves one solves the other. But if they're parallel, they have nothing in common except their slope, which is what makes them parallel. So in a picture, this summarizes what we just looked at. The language for this is that the first system, A, and the last system, C, both of those are what we call consistent systems, which means they have a solution, at least one solution. So as long as the system has at least one solution, we call it a consistent system. In case B here, there are no solutions, and we call that an inconsistent system. So inconsistent systems have no solutions. Now, you can transform a system by multiplying it completely through by the same number. You've always known in algebra that if you've got an equation and you multiply all the way through on both sides by the same number, then you still have a true equation. It doesn't look like it used to, but it really is the same equation. You really didn't change anything about it. So ways you can transform a system of two equations is, for one thing, you can trade the top one for the bottom one. It doesn't matter, which one comes first. There's two equations, and it could be equation 1 and equation 2, or it can be equation 2 and equation 1, and it's the same thing. The other thing you can do is you can multiply both sides of any equation by any non-zero number. And the last one is that you can replace an equation by a non-zero multiple of that equation plus a non-zero multiple of the other one. In other words, don't multiply by 0. But it's still a little hard to see why, what is this talking about? So let's do an example. So what we're going to do is I'm going to walk you through, and I'm not going to show you all those steps at once. I'm just getting the problem here. I'm going to walk you through this. So this is what I start with. And we're going to play a game that I like to play called Kill the Variable. Everybody really hates variables because, math was okay until I started putting letters in it, right? Yeah. That was my daughter's chief complaint. She said, "Mama, why do they have to mix up the letters and the numbers? I don't understand what letters have to do with math." And I felt for her. So what we want to happen here is we would like to multiply straight across on both equations by some number, and I may not choose the way that's in the PowerPoint. I'm going to leave the PowerPoint as it is, but I may choose a different option. We need to multiply both equations by some number so that one of the variables dies. And a variable's dead when its coefficient is 0. right? So what would happen if I multiplied 3 by 11, which would be that 11. And I also multiplied the second equation by 3. That would be that 3, right? Now, nobody's going to die yet, because when I multiply through here, the bottom one becomes 33x plus 3 times 4 is 12y equals 3 times 95. I believe that's 285. Y'all check my arithmetic. Okay. And then when I do the first one, it's 11 times 3 is again 33. Plus 11 times 10 is 110y equals
26.
That's right. Now, nobody dies because nobody cancels each other out. But could I make that happen? Suppose I'd made this 3 negative. That means this is negative 33 and minus 12y and negative 285. Now what happens? That's right, the x's cancel out. Ooh, I forgot the x. So I kill the x. He's out of here. So now all I have left is 2 equations. But those 2 equations have no x's in them. Anybody got any ideas on how we're going to figure out what would work in both of those equations? Solve for y. One way you could do it. The other thing you could do is you could take what you've got, and this is not immediately obvious to everybody, okay? But this is a part of the process that you can think through to do this. Since this is now my new system of equations, it's just that they've only got one variable in them now. What would happen if I multiplied the top one by 12? No, I don't think I want to do that. I don't think I do, because then I've killed everybody off and I have no clue what I'm doing. What would y have to be to make this one work? Hmm? So it's whatever 1265 divided by 110 is. And hopefully that would be the same as what negative 285 divided by 12 would be. Is it? Nope. Hmm? Neither one of them.
I mean, they don't match.
No, they don't match, and they have to match. Ah, you call it on. That's why I popped that back up there. Because remember, the other thing you can do, you don't have to multiply them both by anything. You don't necessarily want to solve them. It says that you can replace any equation by a non-zero multiple of that equation plus any other equation. So we can just add those 2 equations together, right? All right, let's just add them together. So what happens when we add them together? 110 minus 12 is how much? 98. Y equals 1265 minus 285 is what? Now I can solve for y, because this was two separate things down here, but this is only one. And if I divide both sides of this by 98, I get 10. And by what we call back substitution, what we realize then is that if y is 10, then 3x plus 10 times 10 is equal to 115. And since 10 times 10 is 100, 3x is equal to 15. And x then is equal to 5, like we said it should be. Okay? And you can check by substituting back in, not just into this equation, but you can actually go back to your second equation and substitute in y equals 10, and you'll find that the answer to that one is also x equals 5. Okay? Now that's all the algebraic way to do things. And it's the introduction to what's called Gauss-Jordan elimination. And the other thing that we could have done is what they show here. We could have taken 3x plus 10y, one of the original equations, and added the combination of those last two to it and done a little bit more work, which I didn't see the need to do. Because when we have to do it with algebra, I want to be the most efficient about it. So Gauss-Jordan, on paper, with all the variables, is not the most efficient way to solve equations. That's the problem. But we can do these problems with a calculator, and it is very efficient. So what I'm going to do is we're going to solve this system, but I'm going to go ahead and kind of lead you into the next chapter, okay, or the next section. So let's look at the system we're going to solve. Get your calculator handy, because I don't see any reason to belabor something when there's an easier method to do it. So copy down your equation. And its partner. And I will tell you in advance that there is not going to be a solution to these two. Okay? There is no solution to those two. But here's how we're going to do the problem this time. And we're not going to use the graph. We're going to go, now this is different if you're on the 84 or the 83. On the 83, there is a matrix button right next to the math key. On the 84, I'm not sure it's in exactly the same place.
You have to be second, and it's right.
Yeah, I think it's a second.
It's right below that.
Okay. So get to your matrix menu. I'm going to make a few notes for you as we go along. And it's kind of funny the way they spell it. They spell it M-A-T-R-X, because I think they ran out of room. On the TI-83, it's next to the math button. On the TI-84, at least most of them, it is second And then, what's actually on that key below math?
X to the negative first power.
Okay. So it's the one below the math key, so it's second and x to the negative first power. And it brings you to names, and notice that the names are A, B, C, D, E, F, G. A matrix is just a single letter, it's usually a capital, as far as, you know, what you're using it as a variable for. And then there's something that says math, and then there's something that says edit. Just like when we were doing the stuff with list 1 and list 2 in chapter 1, you got to edit first. You got to tell it what's in the matrix. So choose edit. Choose edit. And all of the matrices are essentially the same. It's like that y equals menu to graph with. So we're just going to pick the first one we have. And that's a 1 by 1 matrix, which says it has one row and one column, and it basically is just one number, and that's not much of a matrix. The matrix that we want to make we want our matrix to look like this. This is called an augmented matrix. That line's not going to show up in your matrix, but basically this last column of the matrix is the constants on the other side of the equal. This one happens to have two variables, so you have 2 rows and 2 columns in this part of the matrix. But the dimensions of this particular matrix, it's always rows by columns, and the number of rows we have, remember rows go across the field, is 2, and the number of columns we have is 3. So this is a 2 by 3 matrix. That's called its dimensions. And we have to tell it the dimensions of the matrix first so that it'll open up enough holes for us to put in the numbers. So tell it it is a 2 by 3, and all I'm doing is typing the number and hitting enter, and it moves me through it. And it opens up a matrix that has 2 rows of zeros and 3 zeros in each row. That wasn't you. That was me.
I think I turned something.
I forgot to turn mine on buzz. Now we're just going to enter the numbers in. 2, and notice it goes across the page, so you have to go across the page too unless you use the arrows. 2, be sure you use your negative sign, not a subtraction. Negative 3. The calculator makes a distinction, so make sure it's a negative 3. And then 6, and then it moves down to the next row, so then that's negative 4, and 6, and then 8. Okay? Now what I recommend you do at that point, to keep from getting messed up and in trouble, is press your second and mode key to get back to your home screen and clear it off. If there's anything on the home screen, any arithmetic or anything else, clear it off. Just hit clear. Okay? Once you've done that, one of the things I like to do is I want to make sure the matrix looks like what I wrote on my paper when the calculator prints it out. So I go back to the matrix menu and I choose matrix A, which notice now it says matrix A is a 2 by 3. So I press enter and then enter again because I want to see it printed out. I want to make sure it looks like what I think it does. Now folks, that's the best advice I can give you because I had people in my 1630 class the last couple of years, and when they took their test, they got very frustrated because they had wrong answers, and I would ask them, did you check your matrix? No. Well, put the problem back in your calculator and show me what you did. So they put the problem back in the calculator and show me what they did, and suddenly the right answer would pop out. And that was because they put it in right while I'm standing there watching them. But they didn't check themselves during the test. So, and I'll remind you during the test, check your matrix. Make sure your matrix is right. Because if you give it the wrong matrix, guess what it's going to give you back? Wrong answer. So now that I know my matrix is in there right, there's only one thing you need to do. All of this multiplying and adding and row swap stuff, calculator does it for you. Go back to your matrix menu and go over to the one in the middle, math. Give me the math matrix. And scroll down. To item B. Choose option B, RREF. And then go back to matrix again and choose matrix A and close the parentheses. And after you've closed the parentheses, you can hit enter. This is what it gives me. It gives me back this matrix. And this is how you know that there is no solution to this system. You take that matrix and you put your equals back in. Remember, this is where the equals would have been. Put your equals back in and put your variables back in. If you have no x's and no y's, what does that add up to? Nothing. But it says nothing's equal to 1. Is it? Nope. That's a lie. So there's no solution. Okay? There is no solution to that one. Now, just for practice, let's go back and look at the one that we did to begin with. Your matrix for that looks like, let's go back to matrix, go back over to edit, and this is a 2 by 3. And this matrix starts out with 3, and then 10, and then 115, and 11, and 4, and 95. And then I quit, and I clear my screen off because I don't want to be distracted by anything else. And I ask it to show me matrix A to be sure it looks like I think it does. 3, 10, 1, 15, 11, 4, 95, it does. So then I go back to matrix, go over to math, go down to B, tell it it's matrix A, close the parentheses and hit enter. So that is the equivalent. We write out that matrix. That's equivalent to the augmented matrix 1, 0, 5, 0, 1, 10. So if I put the variables back in that matrix and the equal signs, what that tells me then is that no x's and 1 y is equal to 10. And it says an x is equal to 5, which is what we know the solution was. So when you do reduced row echelon form on a matrix that has a solution, this is where your solution shows up. The way you know that there's no solution is that you'll get zeros on the bottom except for the last number. And the way that you'll be able to tell there's infinite solutions you get a row of zeros on the bottom. And you know, of course, that's true because what this means is that no x's plus no y's is nothing. 0 is equal to 0. And that's true. And it doesn't matter what you put in for x or what you put in for y, it's always going to be true. Okay? So we pretty much learned a really fast way to do all this stuff, and we're just ready now to go on. Now, when we get to the next section, I'll talk to you more about how to write a general solution when there's more than one solution, but I'm not going to worry about it in section 1. We can talk about that in section 2.